So what I hope to do today is finish up 2 sample tests, so we move on to more interesting things. Any questions so far about t-tests? All right, so we were talking about the fecundity data, number of eggs and snails in different parts of the intertidal zone. I think we did most of the calculations yesterday, or on Monday rather. And so we arrived at the final answer here, and then we were going through the R script that basically also verified all of these things. Have you guys been looking at the R script, running the R script on your own, making sure that you know how to operate it? How many of you have done it? Finally got the R script on your own. Okay, those of you who haven't, make sure that you're going and doing that. We're going to start using R more and more and more as we get into more complicated things. One thing that we didn't talk about is a paired t-test. So what are the assumptions that you generally need to have present in order to do a statistical test that is a parametric test that's based on some sort of parameter like a mean? What are the 4 assumptions that you have to meet?
Should be independent, random, variances, and normal.
So the samples should be independent, they should be randomly selected. The variances should be similar. And the distribution of sample means there are times though when the data that you have are not independent. So for example, if you're a professor and you want to basically quantify whether or not anybody learned anything in your exam, what you might do is you might give them a pre-test, and then you might give them a post-test. And then we would have Athos's score on the pre-test, we would have Tom's score on the pre-test, we would have Bryce's score, Maddie, Grace, et cetera, et cetera. And we would have whatever their score was on the pretest. And we would have their score on the post-test. Now, in both of these cases, I know Connor has had some statistical training. Hopefully, if we gave you a pretest, you would hopefully score higher than who in here hasn't had a course in statistics before. So we might expect your score on the pretest to be higher than Bryce's score on the post-test, which means we might also expect your score on the post-test to be higher. But the difference between those 2 scores is probably going to be different. If you started off at a higher level, you had less to learn in reality. Have you learned anything in this class yet? Okay, good. That's a positive thing. You have a lot less to learn though, probably than other people who haven't had any introductions to statistics. And so we would want to take Connor's, prior experience and qualify what his final score on a post-test would be by what his grade on a pre-test might be. Because the question when you take a class, and the question for example, the promotion and tuning committee, if they're looking at your materials, is one way of telling whether or not you're a decent teacher is actually figuring out how much students are learning. You can be really likable and nice and everything else, and your students can not learn anything in your classes. You could be irascible and grumpy and have a class of 7:45 in the morning. Students learn a lot. They're maybe not having as much fun as they would if they were learning nothing. But the difference is, what did you know before you got into that class? What did you know after you came out of that class? because these are two different values gathered on the same individuals, these two data sets are no longer independent. You can't just calculate what is the average pretest score and compare that to the average post-test score, because you no longer satisfy that particular requirement of doing a regular t-test. So what you do is a paired t-test where the values that you have are paired because they're not independent of one another. There is a data set in the materials for last time, and they're also actually in the materials. So they're in the February 24th materials because it's now the 26th. If you go onto Moodle and dig those up, you will find a data file that is called paired t-test. Let me pull this up so we can actually see. So basically, this is exactly what we have. In this case, these are class averages on pre-tests and post-tests for teacher 1, teacher 2, through teacher 20. And basically, the question that you might have at a school, if you were, for example, working in a public school, is, on average, are your students learning things in the classes that they're learning from different professors or not? And so in this case, we have the average score of all the classes that this teacher does of pretest, the average of post-test. In this case, the lack of independence is you have two scores for a particular teacher. And then you can just calculate the difference between pretest and post-test scores. In some cases, the differences are small or non-existent. In some cases, the differences are larger. In some cases, the differences are negative. In this case, students came out of the class actually knowing less than what they knew when they went in, which is always a bad sign. So what you do in a paired t-test is you essentially do a one sample t-test, which we haven't really talked about. In a one sample t-test, what you want to do is you want to basically take whatever parameter it is that you're measuring, and you want to test it against some hypothesized value. In this case, the one sample t-test is you would be looking for some difference that in this case would actually be greater than 0, and you test that against the difference of 0. Because a difference of 0 would mean that students didn't learn anything. A difference that is greater than 0 means that they learned something. And so the question is not, what's the average pretest, what's the average post-test? The question is, what is the difference? D1, D2, D3, D4. And so when you do this, the t-statistic that you calculate is actually pretty easy. It's whatever the average difference is divided by the standard deviation of those differences. And so in a paired t-test, what you do is you subtract one of these values from the other, you get that difference, you average that difference, you find the standard deviation of that difference. The t-statistic is the average difference divided by the standard deviation of the difference. That's what t is. You check that t-statistic against degrees of freedom, which is the number of differences minus 1. And so in that way, it's very much like a t-test. You would look it up in a t-table, et cetera, et cetera. So we could easily do this. I've done it for you here. What this is right here, this is the average. So if you look in the formula bar here, this is the average of all of the differences. This is the standard deviation of all the differences. Oh no, this is not standard deviation, this is standard error rather. I made a mistake. This is the standard error of the differences, my bad. standard error, so the t-statistic for this should be 2.5 divided by 0.6485. So actually, in this way, calculating the t-test in this situation is much easier than doing a two-sample test because the measure of the variation in the data is much simpler measure. It's a measure that you're already familiar with. So we can go to R. So in the materials for today, there's also that two-sample R script that we were working on before. And if you recall correctly, T-Test 2020. In my version of this, the paired t-test is kind of in the middle. I don't know why I put it in the middle, probably because I was doing it without thinking about how it's going to be covered in class. Let me find it. Oh, here it is. So in my version, it's at about around line 51, 53. So there's a data file that is in your on your Moodle site. So you need to have that available to you. When you read this in, you'll actually see that it looks exactly like the data set that we just looked at. It has the teachers, it has their pre-test score, their post-test score, and it has the difference already calculated. The weird thing about this though is that the code for doing a paired t-test doesn't actually allow you to look at it in a data frame. So what we're gonna basically do is we're going to separate out the pre-test scores from the post-test scores. So we're going to basically essentially say pre-test is essentially the pre-post values, but just the pre-test column. So we're gonna actually do the opposite thing that we did before. Before, we took a bunch of columns and put them together in a data frame. Now we're taking a data frame and we're splitting that apart into a set of strings because of the peculiarities of R. And so now we've taken the pre-test scores and we have basically constructed a vector out of those. We're gonna take the post-test scores, construct a vector out of those, and we're basically going to calculate the differences, separate out the differences, and those are the differences there. And so what we wanna have is we wanna calculate the average of the differences, and that should be 2.5, because the code for this is basically, you have to tell it what the post-test is, what the pre-test is, and whether or not this is a paired test. And so, in that way, the structure is very similar to the very first t-test that we did where we had just strings of numbers. And so when we do this, what it should hopefully give us is t-test. So if you divide 2.5 by 0.6485, what do you get? Did anybody do the math? Do the math quickly. You guys have calculators in front of you?
Also, my R script says there's no such file or directory for this one.
Okay. That is because, where is your data file? Where did you put your data file? Show me.
That's it.
Yeah, so you got, so you
Oh, is it
download,
this one?
yep, it's that one.
Oh, I need to put that in
You need to put it there, yep.
Okay.
Which one is it?
Paired T.
Okay, that
So
was-
it's probably doing that, usually when you get that kind of an error message, it's because you're running your R script in a place where your data are not, so you either need to tell R where to go and find your data, or you just need to put your data in the same place that your R script is. So where are you running your R script from?
Honestly, might be my downloads.
Yeah, so go to just so you download it from there.
Yeah, so.
Alright, so go to Husband Find Things on that machine. Where's your file explorer? Where's File Explorer? So you've downloaded the R script, you haven't downloaded the data file, so just download the data file. And put it in that same place and you'll have it, sorry Grace, you were saying something?
I put it in here.
Okay. Okay, so, and that's where you open the script from? Is that where you open the script from?
Oh no, I think it's from here. So should
Oh,
I
yeah, yeah,
just
so close the script out. Just close it out. Or open the script.
Wednesday.
Now go down to line 53 or whatever. So load that thing out. There you go.
Okay.
Hmm?
So can I not download this like from?
You should be able to, just click on that. Oh, that's weird. Did you download the folder earlier? You said you thought you did. Okay, so this is now, it's in your download, so you should be able to, where's your R? Close the R. You should be able to just open this from here, since your data is in the same folder. Go back here to line 3, see if that will download the data file. Let's see, that doesn't work. It's in desktop folders now. We should work. Yeah, it's working. So go to pre-post, it should give you the data file. Activate pre-post. Yeah, there you go.
Thank you.
Yeah. This 2.5 divided by 0.648, is it 3.8649? Awesome, so we did our calculations correctly when we did them in Excel by hand. You have 19 degrees of freedom because there were 20 faculty members, and so your degrees of freedom is 1 minus the number of paired samples that you have. And then the p-value is significant, which means that at least as determined by a t-test, a average learning of 2.5 points difference between a pre-test and a post-test is a significant amount of learning. Now, if you were making educational decisions, you might argue whether or not 2.5 points difference between a pre-test and a post-test is a significant amount of learning. But in this case, these are statistically significant differences between the pre-test and the post-test. And this is the tricky thing about this. A t-test, test against a difference of 0, But the fact of the matter is you could test against any given difference. You just have to tell R what the difference is that it needs to surpass in order for you to consider it significant. And so usually when we think about what the null hypothesis is, we think about the null hypothesis being a difference of 0, but that doesn't have to be that way. You can determine what a significant amount of learning would be and ask, okay, have these teachers surpassed that expectation? Just the default typically when we're thinking about things is a difference of 0. So paired t-tests aren't really that different from a regular t-test. The only thing is you calculate it slightly differently because you're not dealing with data that's not independent of one another. And that's all we have to say about t-tests, because guess what? I learned how to do t-tests when I was an undergraduate. You know how many times I've done t-tests in the real world? Never. I've never done it in the real world. The only time I've ever done them is when I've taught other people how to do them. So, the important thing about t-tests is if you ever need to have it, it's available. You can actually get the same answer from doing more complicated methods that are just overpowered for dealing with 2 samples, but you could just as easily do this with the routines that an analysis of variance does, and that's what we're going to do next. The important thing that I want you to get out of t-tests is not just how to do a t-test, but the idea that there's always some measure of variation among means, and in this case, it's among 2 means, and there's always some variation within means. And the test statistic that you calculate, whether it's a t for a t-test or whether it's an f or an ANOVA, it's always some ratio of how much variation is there among means divided by how much variation there is within means. This is a core concept that you need to get stuck in your heads to proceed through the rest of the semester. Analysis of variance operates this way. Regression operates this way. Analysis of covariance operates this way. Every test you will ever do operates under the same core principle. What's the variation among means divided by the variation within means? Over and over and over again. You've now learned everything you need to learn in applied statistics. How you calculate variation among means and how you calculate variation within means. The details of that are slightly different from method to method, but it's still this core idea that there's a certain amount of variation among the things that you're trying to distinguish, and there's a certain amount of variation that is trying to obscure that view. Wouldn't it be nice if we get to the 5 weeks, the beginning of the first 5 weeks, and we're just like done with what we needed to do? Yes, sir.
How can I compare my results in a t-test to like, for example, I set a 50% of increase of grades, okay, in a t-test, okay. So the program should give me a variable.
Yeah, so I haven't actually done that. Well, okay, so this is the difference. So the t-test is a test of a difference of of 0. So
Okay.
if we run this,
You give
basically
me
it's
3.8.
saying this is the t-statistic for a difference of 0 given, wait a minute, did I do that right? Yeah, so this was a t-test on the differences. So we just did a t-test. We constructed a data set here that is just the differences. So we can run a t-test on those differences. So if we observed a difference of 2.5, but we actually don't think that you're doing good teaching unless there's an increase of at least 10 points, we wouldn't test this against a difference of 0, we would test it against a difference of 10.
Yes.
And so what we can do is we can tell R, well, what's the level of difference that we would need to see to find significance? And when we do that, we would find that clearly, oh no, sorry. That's not telling us what we wanted to tell at all.
Yeah, he changed the value of t from 3 to -11.
Yeah, this is the observed difference, so how would we, I've actually never done it where I've changed the null hypothesis.
Yeah,
I would have to figure that out, but in theory, you should be able to tell it what you want it to exceed or not.
Yeah, because I was thinking about that, like, for example, a public school system, such as in America or whatever, they want to increase this value of like learning
Oh, yeah.
professors. So they set a goal for 30%, and yeah, in the end of the year of the period of schools, they make the t-test and see if this.
Yeah, so I don't know how to do it, but I can figure it out by the time I see you again. I'll figure that out between now
No
and
problem.
now and then. There should be a way of saying what's the hypothesis hypothesized difference that I want to exceed. I just have never done it, and so.
Super important that, right?
Well, yeah, so I should figure out how to do it. Okay, other questions about t-test? All right. I don't want to say that. All right. You guys follow the news? You guys news followers at all? You guys should be news followers. It's a very important year. Why is it a very important year? What's that?
The election year.
It's an election year, isn't it? You can hardly listen to the news on radio or television or anything else without escaping and hope to escape news about politics. What's coming up in South Carolina? So the South Carolina primary is coming up. Thank God it's not a caucus. The caucus in Iowa is basically an abysmal disaster from a logistical standpoint. Have you been following the news coming out of South Carolina about the Democratic nominees? No. What is Biden hoping?
Needs a win.
Oh my gosh, he needs a win because he lost. He finished 4th in Iowa, 5th in New Hampshire, a distant 2nd in Nevada. And so what is former Vice President Biden hoping for in South Carolina? Hmm? He's hoping to win. What's he banking on though?
He's banking on African American voters.
He is banking on his popularity with African American voters. And so when you think about real world applications of statistics, one of the things that you could do is you could actually survey people's opinions about a wide variety of things and divide them up by socioeconomic class. You could divide them up by racial differences. You could divide them by gender differences, et cetera, et cetera. And in all of these cases, you would want to be comparing something like the average responses of, for example, white people versus African American people versus Asian people versus Hispanic people versus other, whatever the category other might be. And in this case, if we're comparing the responses of white people, Hispanic people, African American people, Asians, Native Americans, et cetera, all of a sudden, we have way more than just two means that we're talking about. And so if we want to see if people are thinking about different issues based on these course scale, in this case, racial and ethnic guidelines, divisions, we can't just do a bunch of t-tests. We can't do a t-test that compares, what people are like, white versus Hispanic, white versus African American, white versus Asian, white versus Native American, Hispanic versus African Americans, Hispanic versus Asians, Hispanic versus Native Americans, et cetera, et cetera. Why not? Why can't you just do a bunch of t-tests to see if there are differences among these different groups of people in any kind of metric that you might want to compare them with?
To lose time.
No, it's easy. We could do it in just a few minutes in R because R is a computer and it does things really fast.
Yes.
Let's say I wanted to look at, well, I was a socioeconomic person and I wanted to look at mean incomes of white people versus Hispanic people. I could just gather up a bunch of white people, ask them how much they make, then I gather up a bunch of Hispanic people, ask them what they make, African Americans, ask them what they make, Asians, ask them, Native Americans, ask them. I would have samples of each of these things. I could calculate their average incomes, and I could see whether or not white people make more than Hispanics, et cetera, and I could do that with a bunch of t-tests. Why would I not want to do that? It would not take forever. As soon as we have the data, it would take moments to do it on a computer because computers are fast. It would take you a little while to do it by hand, but whenever we have to do something big, it's better to do it on a computer. When you do a t-test, what do you test that statistic at? An alpha level of 0.05 and degrees of freedom that is equal to the number of subjects minus 1, right? Correct? What is alpha again?
Type 1 error.
Type 1 error. What is type 1 error?
Saying they're different when they're not.
It's the probability of concluding that two means are different when actually they're not. So we could do a t-test for white people versus Hispanics. If we were looking at income, we could do a t-test of white people versus African Americans. We could do a t-test of white people versus Asians, white people versus Native Americans, Hispanics versus African Americans. For each of these, what is the type 1 error? It's 0.05. It's 0.05 for this one. It's 0.05 for that 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 one. How many comparisons do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? 10. Right? 10 comparisons to do all possible comparisons. Do you know what the overall alpha level would be for those differences if we did each of these things as 10 t-tests? Probabilities, do you add them up? Do you multiply them? How do you add these independent probabilities? How do you get an aggregate probability?
Additive, right?
It would be
It's a
additive.
50%.
So 10 times 0.05 is 0.5. And so if you did 10 independent t-tests on these data, if you concluded that any of them were different, you would have a 50% chance of making a type 1 error. Do you want to say two groups are different in terms of their income when they're not at a 50% rate? No, probably not. So the reason you can't just do multiple t-tests is type 1 error rate gets big fast. It gets to a level after just 2 comparisons that is generally unacceptable by modern standards, because type 1 error is additive textbook homework for Friday, go and look up in the index what the Bonferroni correction is. I forget if it's spelled with 2 R's or 1 R, but there's a Bonferroni correction. Just look it up, learn what it is. We're not going to talk about it in detail now, but the fact that there is a thing called the Bonferroni correction and what it does is indicative of what this problem is. That when you do lots of independent tests, the type 1 error rate across those tests is all added up. It's an additive process, which leads you very quickly to making decisions that are probably wrong if you're doing statistical decision making. This is why we need other methods, and this is why we need, in particular, an analysis of variance. At the beginning of this, PowerPoint presentation, there's a quote that I pulled from a guy talking about his experience with R. Yesterday, I spent about 6 hours, 6.5 hours, closer to 6.5 hours, working with animal behavior students in my animal behavior class, working through a 747 line batch of R script. 3 hours was in the lab with the students, another hour and a half was in a couple of students after lab who came to my office, and then I got lunch finally at like 1:30 because I was feeling a little low blood sugar level, and then I had students in my office after that, such that by the end of the day yesterday, I had essentially spent about 6.5 hours with animal behavior students, helping them get over their profound fear of R. R is a little challenging, it's new to you, et cetera, et cetera. I know some things about R, I don't know everything about R. I ran into a number of issues when I was building this R script for my students because it was a type of data set that I had experience with in the past, but for whatever reason, when students gathered the data in the same experiment this semester, there were a bunch of outliers that were throwing the data off. And because it's not a standard statistical kind of test, I had to invent a new way of visualizing the data so that I could actually detect where the outliers were and what to do about them. And so it took me a lot of work to work with it, but then once I had it worked out, when I presented it to them and was walking them through the R script, they found it daunting. So this is just a quote that basically says, even if you think you know something about R, chances are there's somebody out there who knows a lot more about R than you do, and you're going to make all kinds of stupid mistakes over the course of time. I make them myself. On the R script that I was working with my students with yesterday, I actually needed help from another person to figure out how to do this outlier detection. And so the thing about R, when you get stuck on something, come get help from me and we'll try and figure it out. Between the two of us, if you happen to have a wife or husband who's an expert in R, that's really nice because you can just ask them across the kitchen table. And don't get too stubborn thinking that you can figure it out on your own, because you might eventually be able to figure it out on your own, but chances are you'll be able to figure it out quicker if you have some help from somebody. So this is a data set. This is an actual data set of what has to be the most ridiculous experiment that I've ever read about in science. These scientists wanted to know what would happen to plants if you gave them different kinds of water. And normally when you fertilize plants, you would take fertilizer, you would mix it up in water, and then you would water that plant with the water that has fertilizer added to it. But normally fertilizer has things like nitrogen and phosphorus and potassium and sodium and calcium and things like that, nutrients. These people wanted to look at sugars, strangely enough. The weird thing about adding sugar water to plants, though, is that plants generally aren't energy limited because they do photosynthesis. They create their own sugar. And so I still to this day don't know why they added sugar water to plants, but they did for whatever reason. So they set up a control where they just gave them plain water. They set up a treatment where they gave them 2% mixture of glucose, which is a simple sugar. It's a sugar with only one 6-member ring. Fructose is a different form of that same simple ring. Gave them 2% fructose solution. Then they gave them a 1% glucose, 1% fructose solution, which then maintains the whole solution at 2%, but now it's a 2% mixture of two simple sugars. And then they gave them a 2% sucrose solution, which is actually, sucrose is a molecule of glucose and a molecule of fructose bonded to one another. So you have glucose by itself, you have fructose by itself, you have glucose and fructose but by themselves, but put together in a mixture, and then you have glucose and fructose bonded together. I'm assuming that they're interested in what's the effect of single sugars versus double sugars on plant growth if you include these things in the water. I'm not sure why you would be interested in that, but as a statistician, I don't need to know why you're interested in that as a plant biologist. All I need to know is what did you do and what are the data? And what are your questions about those data? Now, there are 1, 2, 3, 4, 5 different treatments here. A control and 4 different sugar treatments. How many different combinations would you have if you did these with t-tests? If you examine these with t-tests?
15.
You would have the same 10 that we had when we had 5 racial categories on the board. You would have 10. So just to drive home this point, type 1 error. If you have type 1 error and you combine that across a bunch of t-tests, this is what you get, and at the end you get the sum of the probabilities, which is 0.5, and so we're not going to do that. So what we're going to do instead is we're going to look at data like these. Oh, let's see, where am I? We're going to look at data like those, and we're going to basically use an analysis of variance. The weird thing about the analysis of variance is it's a method that is used to test whether means are different. Why did they not call it analysis of means? This is the easiest question on a test. Thankfully, there are no more tests in this class. Why not call it the analysis of means? If the goal is to test whether or not means are different from one another. Cool.
You still calculate it with the idea like variance among divided by variance within.
That's exactly why. So here we have some distributions. Each of these distributions we are going to collect samples from. Calculate a mean for that sample. We will collect samples from this distribution. We'll calculate the sample mean from that distribution. We will collect, I should have done this one in purple. This one purple. Collect samples from this one and calculate the mean of that distribution. When you do an analysis of variance, what you're interested in knowing is how much variation is there among the means versus how much variation is there within the means. If the variation between the means is small relative to the variation among the means, if the variation among is small relative to the variation within, that within sample variation obscures your ability to see the variation among the means. If the variation among the means is huge compared to the variation within the means, it's really easy to see that those means are different because you don't have all that within sample variation clouding your view of the differences between the means. So an analysis of variance is called an analysis of variance because it's an analysis of two kinds of variation. Variation among means versus variation within means. Why did I not spell it? If within sample variation gets big enough, the 95% confidence intervals get big enough that you could fit any mean on the planet into that 95% confidence interval, which makes it almost impossible to tell one mean from another. If within sample variation is really narrow, 95% confidence intervals are really narrow, it's hard to fit other means into that 95% confidence interval, and as a result, you can tell means apart relatively easily. So it's the ratio of these two types of variation. And there's within sample variation for the purple, there is within sample variation for the red, and there is within sample variation for the black. And it's the summation of all of these forms of variation that you add up to arrive at what's the total amount of within sample variation. You add all of these differences among means to figure out what the total variation among means is also. Those two values then, this gets divided by that, and that's the test statistic that you use ultimately. So, when you think about the hypotheses that you're testing is this mean different from that? Is this mean different from that? Is this mean different from that? That's the hypothesis that you're testing. And the null hypothesis, if you want to think about null hypotheses, is generally the hypothesis that there is no difference. None of these are different from any others. So this is how we would write it in fancy statistical terms. It's population mean of sample 1 different from the population of sample 2, different from the population of sample 3. The null hypothesis is that they're all the same. The alternative hypothesis is that they don't share the same means, which means that they came from different populations, and any one of them could be different, any pair could be different, and it would make the overall analysis of variance significant. Another way of thinking about this is, and a more rigorous way of thinking about this, if you think about the underlying statistical population, it's asking, could this sample have been drawn from a distinctive sample population, or could it have been drawn from the same underlying population? So when you calculate a mean, you're calculating a mean because you presume that that mean came from a particular statistical population. You want to know, did that mean come from that statistical population, and is that statistical population different from the statistical population that another sample mean would have generated? And so we can phrase these hypotheses in the language of the underlying population that we're drawing these samples from. And that's actually how I tend to think of this. Could I have gotten this mean from this other population, or are those two populations actually distinct? So when you think about ANOVA, there are three kinds of variation to pay attention to. One type of variation is in all of this, somewhere, there is, and if I have a different color in here, I'll do it in a different color. Somewhere in all of this, there is a grand mean, which is essentially if you took all of the data in these 3 samples and added them all up without paying attention to what sample they belong to, and calculated the mean, what's the overall mean of the entire data set? And so one form of variation is just how does each of these vary from the grand mean? And how do they vary regardless of whether they're from the red population, the black population, or the purple population? It adds up all these deviations, it squares them to make them positive, and just sums them up across the entire data set.
Don't you lose information by doing that?
No, it's just one type of information. So this is a comparison of each individual data point minus the grand mean squared and summed across everything. That is the total amount of variation within your entire sampling scheme. Now, some of that variation is variation because this purple distribution is far from the grand mean, so all the samples that you draw from the purple distribution are far from the grand mean. That contributes to this thing being big, and that kind of variation is actually variation due to the fact that the mean of the purple population is far from the mean of the overall data set. The red population is relatively close to the grand mean, so it doesn't contribute nearly as much to this summation as the purple population does. The black population is not quite as far away from the grand mean as the purple population is, so it contributes more to this summation than the red population does, but not as much as the purple population does. This brings home the point that there's another form of variation that is a subset of this overall variation, which is the differences of each of the means minus the grand mean. How does this mean differ from the grand mean? How does this mean differ from the grand mean? And how does this mean differ from the grand mean? This is obviously the variation among means. But it never does what I did at the beginning. It doesn't ever calculate the differences between one mean and another mean. It calculates the differences between this mean and the grand mean, this mean and the grand mean, and that mean and the grand mean. Then what's the other thing that we have? We have the difference between each of the values and the sample mean squared, summed across the purple sample, summed across the red sample, and then summed across the black sample. This is the variation within means. Because we're not comparing this to the grand mean, we're comparing this to the mean of the sample that was taken from. This plus this equals that. This is the total variation in the population, or in the samples that you have. Some of that variation is accounted for by differences among the samples. Some of that variation is just variation within the samples. That total variation within the samples plus the variation accounted for by differences among the means goes together to essentially account for all of the variation that there is in your sampling scheme. So what analysis of variance does is it partitions the total variance into variation among samples and variation within samples.
Mathematically, you could add the bottom two together and get the.
Yes, and if you ever see an ANOVA table, one of the first things that you should do is you should add those things up and make sure that they sum to the right number. If you're evaluating whether or not somebody did their stats correctly. The first thing I do is I check people's degrees of freedom. The next thing that I do is I add up their sums of squares. And if one of those doesn't work, then I begin to question whether or not they know what they're doing. Because I'm an infinitely skeptical human being.
does this apply for like huge data sets
Yes,
in comparison with like small data sets?
yes.
For example, when you compare like values, like for example, population in Liberty, Missouri against population in like Chicago.
You can do this, you can do this on whatever sample you want to do this on.
It doesn't matter the size of the samples. And the degrees of freedom and the alpha levels, doesn't matter.
So as you have smaller sample sizes, your overall degrees of freedom goes down, and so your ability to detect differences goes down, because in the numerator of all of these measures of variance that we have is sample size, and as sample size goes down, the overall thing gets bigger, and so you just have more variation because you have small sample sizes.
Which makes sense.
Yeah, and so you can still you can still do the calculations. The question is, can you then detect differences given the sample size that you have? Maybe your sample size is too small to detect the differences that you observe. Yeah,
In this data set, all the sample sizes were the same?
they're all the same, which
Do they
makes
have to
life,
be?
no.
Okay.
And we'll work through an example where they're all the same size. We'll work through the P example, and then we'll work through another example where the sample sizes are different. It alters the calculations just a teensy-weensy bit, and then you have to weight things by sample size, but it doesn't really change any of the fundamentals.
And that slide, just the slideology, am I supposed to read across those bullets?
This is this, this is this, this is that.
The bottom two are.
Comparison of the sums of the square deviations of each observation from the sample mean, that's the within sample variation. Whatever is left over is due to any variation among the means. So this is the total amount of variation. The top one is how does everybody differ from the grand mean? The second one is how do each individual value differ from the sample mean?
I'm trying to track those sets of three with that set of three.
Oh,
And the bottom two seem to be crossed.
they're flipped because I wasn't looking at the slide when I was talking through it. Because I was drawing a picture on the board rather than looking at my screen. So if you know two of these values, you know what the third is. You could know what the total sum of the squares is, and you could know what the among sample sum of the squares is. That would then tell you what the other one is. You can know this one and this one, add them together, and you get this one. Know this one and this one, subtract this one from that one, and it will give you this one. So it's all additive. We shorthand these things. Sums of squares among means, sums of squares within means, and the sums of squares total. Now Tom, I've switched the order of them all together on you, because this is generally how they appear in an analysis of variance table. How much variance is accounted for by variation among means, how much variation is accounted for within means, add among sample variation to within sample variation, and you get total sample variation. This plus this equals that. Don't look at me that way when I write on the screen with a marker. All right. So let's work through this. We're going to take this data set of 50 observations, and we're going to actually work through it by hand. So what's the first thing that you would probably want to know? These are what these data actually look like. I just made a little plot of them. What's the first thing that you would want to know? You might want to know what the sample means are. If you calculate the sample means of each of these things, you will find that the means are located about here, and that's the 95% confidence intervals around them approximately. And so if you think about this just from the standpoint of what you know about the 95% confidence interval, what would you say is different and not in this data set? Is control different from anybody else? Why?
Yes.
Yeah.
Why is the control different?
Yeah, why would you say the control is different or not?
Oh yeah, because 95% of their confidence intervals lie within the others.
So this mean would not fit within this means confidence interval, this mean doesn't fit in this means confidence interval, this mean doesn't fit in this means confidence interval, this mean doesn't fit, and that mean doesn't fit. So you would conclude that the control is different from everybody else. You would conclude the same thing about the 2% sucrose because none of these means fit in that confidence interval and this mean doesn't fit in that confidence interval. But over here, it's a little more ambiguous because these two means fit within their confidence intervals and it looks like they lies just outside of the blue confidence interval. So essentially what an analysis of variance is going to do is it's going to basically test all of these differences simultaneously, but it's not going to do it by comparing this mean to that mean, this mean to that mean, this mean to that mean, this mean to that mean. It's going to compare all of these means to the grand mean, and then it's going to quantify how does this data point differ from the sample mean, this one differ from the sample mean, this one compared to that one compared to that one compared to that, that 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 to that. All of those differences are individually squared and added up to give us the within sample variation for control. That compared to that, that to that, that to that squared, 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 all added up is the within sample variation for 2% sucrose. That compared to that squared, that 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 to that squared, all added up gives us the within sample variation of 2% glucose. Do the same thing for fructose, 1% glucose, 1% fructose. Add all of that up. That's the total within sample variation. Among sample variation plus within sample variation gives you all of the variation that there is that you have in this thing. Pathos.
Is it useful for us to compare like points, like different points, like for example black dot with a green dot? Is there a name for that?
No, you want to always be comparing individual data points to the sample mean.
To the simple mean.
For this data set, do you guys recognize this data set?
Yeah.
Where did you see this data set before? Oh yeah, I'm Trixie that way, aren't I?
Exercise 6.
You already have the mean, you already have the within sample variation for this thing. The thing that I didn't ask you to do is I didn't ask you to calculate the grand mean of the whole data set. But once you have the grand mean of the whole data set, you can then calculate the variation of each of the sample means from the grand mean. So you have almost everything you need to have available for you in that data set, in that you have the means, you have the within sample variation, the sums of squares, the numerators of all of the variance estimates that you calculated in getting to the 95% confidence intervals. Just add those numerators up. You have the within sample variation. You can get the grand mean by just adding all of them up and dividing by 50. That would give you the grand mean. Subtract the grand mean from each of the regular means, square those and add those up, and you have within sample variation and among sample variation, and you can calculate an F statistic. Find the grand mean and the variation, the sums of squares among means by Friday, and bring those in, and we'll continue talking about the P data set. Questions? All right, go to it. We're out of town. So you're doing three things: calculating among sample variation, digging up the within sample variation, and also looking up what a Bonferroni correction is.